Here is your hook for all you young drivers. Take a moment, think about it, put down an answer. If in the course of the lecture you decide you want to change your answer, feel free to do so. Maybe you'll learn something. That's the whole idea of a hook. So if you double how fast you're going, what does that do to the distance it takes for you to stop? The topic that we're talking about, of course, is acceleration. The changing of velocity. Specifically, acceleration is the rate of change in velocity. Just as velocity is not the change in position, it's the rate of change in position, so too for acceleration. That what we're doing is taking meters per second and dividing them by seconds. So the units of acceleration are meters per second per second. This is a perfectly acceptable unit. We are taking meters per second and dividing them by seconds. And when you're working with fractions, often instead of dividing by, we multiply by the reciprocal. So if we multiply by 1 over s, we do have meters per second times 1 over seconds. It comes out to be meters per second squared. There is no geometric meaning to a square second, but these are appropriate units for acceleration. Indeed, these are the ones you will see written most often. Memorize them. So here is again a matching, this time not going from position time to velocity, but from velocity time to acceleration. That, just as was the case before, we look at the slope in this graph, which is the rise over run, and realize that because it is a velocity time graph, the rise is the change in velocity and the run is the change in time. And this, of course, is the definition of acceleration. So it follows that slope in a velocity time graph is the acceleration. And once again, you do not want to be looking at this and saying, well, the velocity is getting bigger and bigger and bigger. You want to talk only about the slope. And you say that the slope is constant and positive. So you would look here for one that had accelerations constant and positive, and so on. You find out which of these letters goes with each of these graphs. Formulas. The first formula that you must memorize, I will not be giving these to you on your test, is this one. And I hope you recognize that that is just your definition of acceleration, algebraically manipulated. So it is not a new thing for you to memorize that delta v was v final minus v initial. So multiply both sides of this by t and add vi, and there you are. The second equation is less pleasant. It's got this awkward 1/2. Got this extra term. Those of you who know calculus might try integrating and realizing that this is the result you get, but we're not supposed to know calculus. So you just ought to accept from me that this is the relationship between displacement and acceleration. Now, I will derive it for you, but maybe that makes you feel better, but it is not necessary. You just need to memorize it. I will not ask you to derive it for me. That here you go. Very important that if the acceleration is constant, then the average velocity is equal to the sum of the velocities divided by 2. But that's only true if the acceleration is constant. That is, the slope in the velocity time graph is constant. And if that is the case, then I can take average velocity and substitute this for it. I'm going to subtract and add initial velocity, a strange thing to do, but I'm just adding 0, so it's legit. And then vi plus vi is 2vi divided by 2. It's just vi. And then you have this 1/2 times v final minus v initial. And then I'm going to take that and multiply it by t and divide it by t. Well, v final minus v initial divided by t is acceleration. And then I'll multiply through this equation by t, and you get the equation we were trying to derive. Only if the acceleration is constant. Indeed, for both of these, only if the acceleration is constant. And it is very important that you realize that. Notice these are naked accelerations. They are not dressed up down here. Is that the initial or the final acceleration or the average acceleration? Doesn't matter. All of those are the same because it is constant acceleration. The next formula is just a matter of simultaneously solving these two so as to remove the time. And indeed, you could memorize these two. There's no need for you to memorize this one, but it comes up so often that I would recommend that you memorize it. It would be a labor saving for you. Here is the derivation. I started with this formula here. Multiply through by t, divide through by a, and I get the v final minus v initial divided by a. And then I take that value of t, solving for t in this equation, I put it in for t in this equation, and you have vi times that thing here. Oops, yeah, here. vi times that expression for t, and 1/2 a times that expression for t squared. And then if you do the algebra and sort it all out, it does come out to look like this. Trust me. If you look in your book, in addition to these three equations, you will also find one where there is no initial velocity. All of these have an initial velocity, but if you solved for initial velocity here and plugged it in there and then solved it out, you would have an equation which had only initial velocity missing, and then you could also solve for a and put it in here and get an equation where there was no acceleration. So there are 5 variables: initial velocity, final velocity, acceleration, time, and displacement, and there's one equation for each of those 5 variables when that one variable is missing. But I don't think it is worthwhile for you to memorize the other 2. The occasion to use them comes up so often. Before we move on, I would like to point out a couple of mistakes that people make, one of which is to try to use this equation, which is very tempting because the units are so nice. If you take meters per second and you multiply them by seconds squared, you do get meters, which is exactly the units here. But this is not a correct equation. This is the correct equation. The other one that people use is they will have a situation where they need to know the final velocity. Most often it's the final velocity, and they will try to use this equation. Big mistake. What I would say is that this velocity is a naked velocity. Right here at its crotch, it is missing its clothing. It's embarrassing. It doesn't belong out in public. That which velocity is that? Oh, and then you suddenly realize this is average velocity. But you're trying to use it to find final velocity. You should never have a v without clothing on. Please hurry to put its clothing on it. That this equation was great for getting average velocity, but if what you want is final velocity, it's no good. I would stay away from that equation. I would write this equation, look at the similarity, and then realize that, hey, there is no acceleration. Acceleration is 0. And then you have that equation that you wanted to write, where this says initial velocity, but that's after all the same as the final velocity, and the average velocity if the acceleration is 0. Don't use this formula. Gets you into trouble. Okay, so let's try using these formulas. And here I've written them out, but please understand that you need to memorize them. The sooner you can get away from the crutch of looking them up every time you need to use them, the better off you will be. And you ought to start right now. Put your hand over top of them and try to do this problem without referring back to those. Okay, a lot of words. And the problem is I want to solve a problem and the words confuse me. I need numbers. And I go looking through all of this and, oh, there's a number. So I write it down. Notice I do not write it with units. As long as they're fundamental units, I'm avoided having other stuff to look at. If this said 5.50, I would not write the 0 because it's more stuff to look at. Just write the number and then you figure out what is that number. And you can look at the units here, meters per second. Oh, those are the units of acceleration. Or perhaps you are literate enough to read this sentence and says it accelerates at 5.5 meters per second squared. So that's the acceleration. Very good. You write that on your paper. This is called à la Houghton, this method of problem solving, where you make this vertical list of everything they have told you in the problem and the question you're trying to answer in the problem. It must be a vertical list or it's not à la Houghton, and I will not give you credit. I will force you to do your problems in this method, in this unit, or you will not get full credit. Thereafter, for the rest of the year, if you find this is useful, after I force you to at least try it, if you find it's not good for you, you don't have to do it that way. But if you get the wrong answer, and I can't give you partial credit, I will not give you partial credit. Okay, so the next number we have is 28. We look at the units, we say, that's velocity, and then we feel so embarrassed. There's a naked velocity wandering around in public. Reach 28. So ultimately it's going to get to 28. That is the final velocity, and don't rest until you have dressed your velocity. Again, I leave the units off. And then the question, here it is, how long? So they want to know the length. That's delta x. I feel like this approach to problem solving is so valuable. And not just for physics problems. If you are trying to solve the problem of homelessness, it is so important before you set out to fix that problem that you figure out, what do you know? What do you know about homelessness? Where does it come from? What does it mean? There are probably many reasons why people are homeless. Well, then one solution is not going to fix them. We need to know all of those reasons. Figure out what it is you know. And then, most important of all, where are you trying to go? What does it mean to you to solve homelessness? Does it just mean putting a bunch of boxes all over the city so everybody has a box that they can get into? Is that homelessness? No, it has to have a roof. Okay, boxes with roofs. Then is it homeless? Then they have to have running water. Okay, boxes with running water and roofs. Is that the solution? What does it mean to you to solve homelessness? And that is a deep question. But it's a question that needs to be answered before you try to solve it. What does it mean? Where are you trying to go? And perhaps you are feeling very awkward because you feel I've made a mistake. That I don't think we want to know how far it goes while it goes up to 28 meters per second, Mr. Houghton. I think they want to know how much time was required to reach that speed, accelerating at this rate. Oh, really? Yes, really. Oh, okay, well, I concede. Maybe I made a mistake. We'll make that say time. But people, how important is it before you try to solve this problem for you to know that it is time I'm trying to figure out? Don't set off to do the problem before you understand where you're trying to go. I promise that I will give you 80% of the value of this question on a test if you can tell me all the information they have told you and you can correctly identify where you're trying to go with it. There's other parts to the problem solving, but this was the creative human part. This is why I hire you, because you are able to make sense of this problem. A computer could take this information and tell me the answer. I don't need humans anymore. It is this that I needed you for, this understanding of what do we know and where are we trying to go. Now, the next step in problem solving, once you've made this vertical list of what you know and where you're trying to go, is which of these tools will work on it. And before long, we're going to have a whole lot more tools, and so it gets harder and harder to choose. But it won't be that bad. Well, I want time, so I can't use this equation. It doesn't have time in it. This equation doesn't have final velocity, so I'll use that equation. Write it. Write it in symbols. You will not get full credit for doing it a la Houghton if you do not write it in symbols first. Don't try to substitute values. That's a false economy. And then you might also pause at this point. I require you to in AP Physics, but it would be a good habit to get into, to say, well, here's the tool I can use. Do I have a right to use this tool? Are the conditions met for this tool? What conditions? The conditions are that the acceleration be constant. And I look back at the problem, and I can see that it was constant. So that's a good thing. It would be well for me to assert I have the right to use that formula. Good job. Okay. And then what I will do is you can be equal. The final velocity, they told me, was 28. Again, do not put the units. They confuse things. S's can end up looking like 5s. Don't write the units. I don't need them. As long as they're fundamental units, everything is cool. And then the initial velocity. And they didn't tell me the initial velocity. Oh no, I can't do this problem without knowing the initial velocity. But how valuable is it for you to know that you need to know the initial velocity? And you go back and you look. There it is, from rest. It started off not moving. The initial velocity was 0. So I add that to my list of the information they gave me. And then I can put a 0 in here for the initial velocity. I can put a 5.5 in for A. The t is unknown. I solve this for t, and the answer I get is that t is equal to this quantity. Then I go back to the original problem, not to this list where I may have left off zeros that weren't needed. And I see that I have 2 sig figs. So I give my answer to 2 sig figs, and then finally I am careful to put the units on it. That is Mr. Houghton's method of problem solving. It is not a waste of time. It is not busy work, and I want you to experience that. So off you go. Here is another problem for you to do. Finally, one for you to do. Cover these formulas if you can, and do it yourself without referring to them. Make the vertical list. Make it over here on the left. I don't want to see vertical lists on the right. That indicates I did the problem and then I made the vertical list because stupid old Mr. Houghton wants me to do that. You don't want me to think that you think I'm stupid, do you? Do it in the right place. And yet another problem. Please do it. Succeed. Units on your answer. The right number of sig figs on your answer. And this problem, these dots are equally spaced in time. They show the location of Mary's car. And she's going at 60 miles per hour. She comes to a complete stop in 4 seconds. and then she gets back up to 60 again, but it takes twice as long for her to get back up. Which one of these pictures is 1, 2, 3, or 4 fits Mary's scenario? Thank you.